Hello and welcome back. We are getting close to the end of Chapter 2. Chapter 2.9 was by far the longest. These last two sections aren't going to last very long. So we're going to talk about other applications of calculus and how it applies. We're going to talk about the tangent line approximation. The idea behind this is a tangent line, once again, is a line that touches a graph at exactly one spot. And if we use this graph here, what we're looking at is we are looking at this specific spot here. And the red line that you see, or pink, or whatever color is that we're doing there, see if I can highlight that a little bit better. And that is touching the blue graph at exactly one spot. Mine's not so good, so we'll leave it with the original. And the idea is the pink line is going to be a good estimate for the blue line. We make this our x-axis here. And we can see when we have an x value, one on the line, one on the graph, we can see that the line is a little above in this case. Sometimes it'll be a little below. The point is, we want to be able to use this line for specific values of x, and it looks like we have a very limited set of boundaries that we can do here, where that pink line is going to actually represent the blue curve as we do that. And ideally, of course, the closer we are to A, the more accurate that line is. The reason is because we would like to estimate all of our answers using a straight line, which is a whole lot easier for us to deal with. The whole idea of this is built on the idea of slope-intercept form. And believe it or not, this here is slope-intercept form. This is actually, if you remember point slope form, is here. And if I add that y to the other side, I get y sub 1 plus m x minus x sub 1. And that is precisely what we have right here. They're using f of x, I'm using y's, but it's the exact same formula as we're looking at that. And again, the idea is our x values need to be close to a. The further away from a we get, the less accurate we're going to have. All right, so let's jump to an example. I'm going to use a separate sheet for this one. And our example here. And we're going to start here, which is our f of x, which is the cube root of 245 x to the third plus 98. And I would like to point out that this is the same thing as saying 245 x to the third plus 98 to the 1/3 power, using our exponent rules as we look at this. And the problem specifically says, find the equation of the tangent line to the graph of the function at x equals 1. Okay. Well, the first thing we're going to have to do is find the slope, which we know is f prime of x. So we're going to have to take the derivative. And 1/3 minus 1 is negative 2/3. And I need to use the chain rule here, which means I need the derivative of the inside. So I need 3 times 245. And I'm getting 735. X squared. And I'm going to clean that up a little bit. Let's take that 735 divided by 3. Okay, so we are going to end up with that 1/3 is gone. So we're left with, what were we left with? 245 x squared times 245 x to the third plus 98 to the negative 2/3. And they say specifically, we want to evaluate this when x equals 1. let's see what we get. So 1 squared and 1 to the third, of course, is just 1. 245 plus 98. 245, oops. 245 plus 98 is 343 raised to the negative 2/3 power. Let's see what we get. This, of course, becomes 245 divided by 343 to the 2/3 power, and let's see what we get. Of course, it comes up to a nice, beautiful, pretty whole number. So there's our 5. That is our slope of our tangent line. I also need to know what f of 1 is, meaning back to the original function. It's cubed root of 245 times 1 cubed plus 98. So this is going to be cubed root, and again, that's 343. So 343 raised now to the 1/3 power. Oops. And I'm getting that this is 7. So we're at the point 1,7 with a slope of 5. So let's build the equation of the line. Y equals mx plus b. We have an x, we have a y. It looks like b is 2, which means our linear approximation is going to be 5x plus 2. So there is our first answer. It says use the tangent line to approximate f of 1.1. So L of 1.1 I'm getting 7.5. And we know that f of 1.1 is going to be, so let's go back to our original functions. So we're going to do 245 times 1.1 raised to the 3rd power plus 98. And then that's going to be raised to the 1 divided by 3 power. Right, so we are getting, this is about 7.513132547. By the way, our second answer in the actual homework is that 7.5. And what I'm doing is I'm moving on to the third part, which wants us to find the error, meaning our error is going to be the difference between f of 1.1 and L of 1.1. So 7.513132547 minus 7.5, and this is going to get us our error. So I'm going to go this minus 7.5. So our error is about 0.01313. So that is our approximated. That says at least 5 decimal places. 1, 2, 3, 4, 5. Okay. And so we, of course, are expecting an error. It's going to be off a little bit because we're not exactly at 1. So it'll be exact at 1, and anywhere any variance from 1 is going to create a problem. And that brings us to page 2, and I'd like to go back to, so this is going to be elasticity. I'm going to go back to our notes. We know that demand functions are decreasing. So when the price increases, the quantity demanded goes down. But what about revenue, which is price times quantity? When the price increases, will the revenue go down because the demand drops so much, or will the revenue increase because the demand didn't drop very much? So picture this. Right at this exact moment, there is a dark chocolate candy bar with pistachios in it from Dubai. Um, and it is outrageously priced. And it's like $12 for a small one and $21 for a bigger one. And the price is high, but the demand stays high. So just because the price goes up doesn't mean that you're going to lose revenue. In this case, because the demand is so high, you're just going to make more money because you're charging more. Whereas there are some other things that, for example, maybe gasoline or something, where when you go to buy it, maybe if the price is high enough, you're going to buy less of it. And so the demand goes down because the price is so high. So as the price goes up, the demand goes down, which means the overall revenue goes down. So is it the case of the candy where the price goes up and the revenue goes up? Or is it the case of the maybe gasoline where the price goes up and so the revenue goes down because people are buying less of it? And that's what elasticity is. Elasticity is a demand of demand is a measure of how demand reacts to price changes. It's normalized, and that means basically it all breaks down to a percent. And our big piece here is this formula here. This is our big one. And what this is so this means that Q of P is our function, meaning P is our independent variable, and Q is our dependent variable. And if we do this ratio, including with the derivative dq over dp, if E, and it's absolute value, by the way, so it doesn't matter if it's negative or positive inside, we're going to make everything positive. If E is negative, then we say it's inelastic, which means the rising prices increases revenue. So this is going to be, in the case of the candy bar, the more expensive we make it, the more money we're going to make because the demand hasn't changed very much. The opposite is if E is bigger than 1, then it's elastic, meaning as prices increase, our revenue decreases. So the solution to that is we got to lower the prices. And if E equals 1, then we're right at that breaking point. All right. So I can stay, I think I have enough room to do this in this here. So we have a demand function, d of p is equal to the square root of 200 minus 2p. And we're going to find the elasticity. So I am going to need d over dp, which is its derivative. And I'm going to very nicely notice, be careful with the chain rule. This is going to give me negative 1 over the square root of 200 minus 2p. So there's my dq or dt in this case over dp. And so our elasticity is going to equal p over q, which is our 200 minus 2p. And that's going to be times negative 1 over the square root of 200 minus 2p. And I am going to notice that this gives us negative p, and the square roots go away. And they specifically want to know when the demand is at a price of 81. So E of 81. And I'm going to get rid of the negative because the P becomes irrelevant. The negative P. 81. 200 minus 2 times 81. Oops. see, 200 minus 2 times 81. And so it looks like we're getting about 2.1315, we'll say. And the point is, this is bigger than 1. So if we go to our grid up here, if it's bigger than 1, then we say it's elastic. Oh, I didn't write this in here. So this should be our 2.13158 about, which is bigger than 1, so it's elastic. And based on this, remember, elastic means that as the price goes up, our revenue goes down. So our solution in this case is to lower prices. If it was less than 1, we would keep prices unchanged, or we would even raise prices. Keep prices unchanged would be if we got that 1 or something close to 1. All right, so we have one more. So we have a new demand function. So I'm going to utilize this room up here. So this is for our new function d of p. So d prime of p for this function is just -8. That's no problem. So we're going to find our elasticity. So this is going to be p over our original function, -8p plus 111 times -8. So we are here. And once again, they want to know specifically when we are at p equals 6. Let's see what we get. And again, because it's absolute value, we're just going to write the positive version of that. And the point is, this is less than 1. So our elasticity, in this case, is 0.7619. It says go to 3 places, but we can go to 3 places. Let's do that to 2. And at what price do you have unit elasticity? Okay, what does that mean? That means what happens when that equals 1. Well, if you remember, first of all, we're assuming p is positive, so the absolute value of -8p is just 8p. Right, and if you remember your algebra, this means that either 8p equals -8p plus 111, or 8p equals -8p plus 111. In this one, we have a problem. Because all the p's go away. So this is definitely not the case. So we're going to go ahead and cross that out. However, this one is going to give us, when we add the 8p to the other side and divide by 16, I'm going to get that p is 111 over 16. Which is about, let's see what we get. Uh, 6.94. And this is asking us the price. So this is $6.94. Means that we're going to have unit elasticity, meaning we're going to exactly equal 1. So we had one example of both, one where it was bigger than 1, one where it was less than 1, and we handled it in both cases. So it doesn't say, but I'm going to go ahead and give a little hint here. This means we should raise prices. That way we'll get more revenue. We'll make more money off of that. And that is going to do it for this section. Nice, small, easy section. Thank you for coming.